This is a video for AQA Discrete Mathematics, Game Theory, Section 2.3, Solving a Game as a Linear Programming Problem. In a previous video we saw how this game here, 3x3 game, could be set up as a linear programming problem. Firstly, by adding 5 to each of the values, so that we were to then maximize the value of this new game, p, which is v minus 5, would give us the value of the outcome to a. The constraints came from looking at each of the possible outcomes in turn for x, y and z being played by player B. So we have this system of equations, maximizing p, which is v minus 5, where the constraints are given by these equations. The constraint at the end here is the total probability. Remember that that was less than or equal to 1, and as long as we do things correctly, that will turn out to be equal to 1 in the final outcome. And finally, don't forget the non-negativity one, that p, q and r are all greater than or equal to 0. We're going to look at solving this using Simplex method. So the first thing to do is to introduce slack variables into each of these equations to change them from inequalities to equalities. So we're going to introduce slack variables into these equations here. And you can see that that's been done on this line, this slide, where we've introduced s, t, u and w into the equations so that the inequalities are now changed to equalities, 0, 0, 0 and 1 for the one concerning the total probability. And so now we have extra non-negativity constraints that s, t, u, w, those slack variables, are all greater than or equal to 0, as well as p, q and r themselves. This can then be put onto a Simplex tableau. So this is the tableau that we end up with, and you can see here that the values that have some number at the moment, so p is equal to p minus v is equal to -5, and we can see therefore that we've got 0s and 1 in this column. The other ones, s, t and u, all got 0s and 1, and at the moment we've got s, t and u equal to 0 and w is equal to 1. Now what should happen ultimately, of course, is that w will be equal to 0, so that we can then find the values of p, q and r equal to giving us a maximum. So at the moment p, q and r are all equal to 0, as is indicated by their columns having numbers in them. And also v is equal to 0, so we have a value of p equal to -5. The objective row at the moment is obviously the top row, and you can see that there's a negative value in there, -1, and that would indicate therefore that we can do better than that. We can make changes which will increase the value of p. And that would be then done by looking at iterations using the Simplex method, and that you should revise if you're not sure what's going on. Revise that by looking at the videos about Simplex method and solutions of linear programs. We're not going to go through the solution of this, but what you might like to do before proceeding is to work through the solution yourself to see that ultimately you end up with the situation on the next slide. So here's the final tableau that we get, and we can check now that in the objective row you can see there are no negative values, so we know that we have reached our maximum value. So having reached the maximum value, we want to be able to then interpret this tableau. So let's go through one at a time. If we take V, for example, then the 1 here indicates that V is equal to 5, and of course P was equal to V minus 5, so the outcome to player A is that they should achieve a payoff equal to 0 in the long term. In other words, if they play the mixed strategy correctly, both players A and B will have a 0 outcome in the long term. So what is that mixed strategy? Well, from again looking at our table, the value of P is equal to 3 over 7, so P is 3 over 7, and P was strategy P, so they should play strategy P with probability 3 over 7, Q 4 over 7, and then we see that for R, then R must be equal to 0. So we get that player A should play strategy P with probability 3 over 7, Q with probability 4 over 7, and R with probability 0. So should never play R. The other slack variables then, ST and W, are equal to 0. So ST, W are equal to 0. But we can see that U, the one slack variable, has a value of 11 over 7. So there are those values highlighted. Remember that if there are zeros and ones in a column, then the right hand side gives us the value corresponding to the position of the 1 in the column. So for V, for example, it's 5. Any column where we've got numbers other than zeros and ones, these all have value equal to 0. So R, S, T and W are all equal to 0. You should also remember that V is the value of this particular game, this tableau, and that the original game we need to subtract 5 from that, so that P here is the value of the original game. So P equal to 0 is the payoff to A in the original game. So A's payoff for this particular mixed strategy. So when A plays P with probability of 3/7 and Q with probability 4/7. Remember that in interpreting the solution that originally we added 5 to the values, so we must always remember to subtract that at the end. So that we have these values for our original solution. V here is the value V in our simplex minus 5. So this is equal to the value of P that we had in the simplex tableau. We had these solutions, which mean that we've got A would play strategy P with probability 3/7 and Q with probability 4/7 and should not play R at all. And the value of the game to A is equal to 0. And as I said earlier, this means that A in the long run would have a 0 outcome, and so therefore B would also receive 0 in the long term. In summary then, we can solve m by n zero-sum games with the following process. We must first of all check for a stable solution, but if there's no stable solution, we need to go for a mixed strategy. Always remember that dominance may reduce the size of the game, and if we can get it to a 2 by n or n by 2 game, then we can use graphical methods. The first one, 2 by n, just sketching directly, and n by 2 we can first transpose and then use graphical methods. If that doesn't happen, however, then we can formulate as a linear program and solve the linear program using simplex algorithms. In reality, then, linear programs are not going to be solved using the hand methods that we've been looking at, so computer software is usually used for solving a linear program. Well, that's the end of this video on the solution of linear programs, and it also concludes the series of videos on game theory 2.